And then if he's
All right, it's good.
Looks all right?
This will zoom?
Yep.
Oh, okay, good. Yeah, we're good.
Okay, here, let me toss you a candy. All right, let's see, are there any questions? All right, let me just briefly review some of the things that we were doing last time. I started out just by saying what the definition was of a group. I don't think we need to review that again. Although I could mention that physical transformations or any kind of transformation naturally form a group. And automatically do so if they leave something invariant. Let's open these windows. Well, at least raise the shade. One of the advantages of New Mexico is daylight, and we might as well use it. So, we've been labeling group elements by some parameters, and by that we mean that if we have a representation d of alpha, then d of alpha is an exponential of I times the sum of the generators. And let me see, where did I put the subscript on alpha? Did I go up or down? I think down. Okay, so the T alphas are matrices. The exponential of the matrices then gives you a matrix. If the T alphas, if the TAs are Hermitian, then this is unitary, but and then the group is compact. But in general, some of the T's are Hermitian, some are anti-Hermitian, and that's your general group. Now, one of the key observations last time was if we had e to the epsilon TB, e to the I epsilon TA, e to the minus I epsilon TB, e to the minus I epsilon TA, then this was 1 plus epsilon squared TATB, and that had to be some linear combination of epsilons. And so this has to be 1 plus I epsilon squared, some constants, FCAB, TC, and it has to be, this is the approximate form, but this form is exact, and this has to equal some e to the I epsilon squared FABC TC. Right. And so these things, these F, C, and D are called the structure constants. Every group has them. And if we choose to adopt the exponential parametrization as a way of labeling elements in the group, then the fact that every every representation of the group has to obey the multiplication law. In other words, the multiplication law here is G of alpha sub epsilon and B. G, actually this is G inverse. G inverse of alpha sub epsilon and A. G of alpha sub epsilon and B, G of alpha sub epsilon and A is equal to some G of this new alpha epsilon squared, and it's actually FC AB TC. Okay, it's this parameter, it's the parameterization, in other words, where alpha sub c, alpha sub epsilon squared c is epsilon squared FCAB. AB being fixed by the choice over here. So in other words, the group rule is this. In other words, effectively, this is mapped into that, this is mapped into that, this is mapped into that, this into that. The product then is approximately this, and so I think in fact one can say it's approximately this, and is equal to it in the limit epsilon going to 0. And that means then that this must hold that any representation, since a representation must respect the multiplication law, we have any d, d1 for example, of alpha epsilon b, d1 of alpha, actually this is the inverse one, and so there's a, how did I say this? Yeah, actually I should have done this. Then we would have alpha epsilon a d1 alpha epsilon b d1 alpha epsilon a is approximately then d1 of alpha sub epsilon squared, and whereby alpha epsilon squared let me put a c there. What I mean is this. And moreover, D2, any other representation, D2 has to satisfy the same rule. And because this is only if we choose to use exponential parameterization, which I can barely pronounce, all the time. And but that's the convention, to use them all the time, to use that parameterization all the time. And if we do, then what you see is that if we switch to D2, then we would have a different set of generators. But the different set of generators would have to satisfy epsilon squared TATB would be I epsilon squared FCAB TC. In other words, what changes is the generators, but these constants here don't change. Okay. So once we adopt that, then the generators are, the structure constants are independent of the generators, and everything then is defined by this relation. And we already made these generators orthonormal, so we had basically the trace of TD dagger, say, to be K delta BD. And this K is specific to the representation. And the reason why we have to have K specific to the representation is that we want the structure constants to be the same for all representations. And that's because we want everything to be simple, so that the parameterization is always the same, this exponential parameterization. So now if we apply this trace relation to this rule here, what we have is that the trace, my traces look a lot like A bar. Anyway, the trace of TATB times TD dagger is IFCAB trace of TC TD dagger, and that's IFCAB K delta CD. And so we can identify the structure constants FCAB as minus I over K, trace of commutator of TA with TB, TA with TB times TC dagger. Okay. So this is our formula for the structure constants. And so pick the generators in any representation, form the commutator, do the adjoint, take the trace, divide by the K of that representation, multiply by minus I, and you have to get the same structure constant.
Is the minus I there to deal with eventual sign issues, or does that come in there naturally?
The minus I, what happened here is, you see, this thing is 1 plus epsilon squared TA TV. And we conventionally, because we're in a physics department with this fetish about Hermitian generators, what we do is we write it this way, TC with an I. We factor out the I, that's conventional. And then we define the structure constants that way. Now, this fetish, though, for general groups doesn't make the T's Hermitian. We pull the I out anyway, and it's only for compact groups that these T's will turn out to be Hermitian. So it's a notational convention, and that I then becomes this minus I.
Okay.
And yes, you've got a candy after you ask the question.
So are there representations that with the structure
Another
constants?
hungry student.
Well, so are there representations with the structure constants with a 0?
Well, some of the structure constants will be 0, not all of them. I mean,
Okay.
Because after all, if a representation has n generators, then there are n cubed structure constants.
Okay.
First. Secondly, if the group is abelian, then all the structure constants are 0.
Okay.
Abelian, named after that man who was only alive for 27 years, Niels Abel. Such was medicine back then, in the 18th century, I think. Maybe the 19th. I think it was the early 19th century.
He has an ODE or a class of ODEs named after him too, doesn't he?
What's that?
I said he has an ODE or a class of ODEs named after him. Isn't there Abel's equation? Is that the same guy?
Well, I don't know about what he did with ODEs, but it is true that people studying the earliest studies of continuous groups, I think, might have been in the context of differential equations and partial differential equations of type 12. Anyway, I'm unsure. I'm A, not a mathematician, and B, not an historian. So, yeah, it was early 18th century, Niels Abel. Okay. So these are our structure constants. Now let's learn a little bit about them. I already mentioned that the structure constant, that these T's, in general, they're just arbitrary n by n mate. Well, I say n by n, depends on the n. You could have little n generators, and the generators could be m by m, say, matrices. In any event, they can be either compact or non-compact. And you see, if you have an arbitrary matrix, you can take A plus A dagger, that's Hermitian. You can take A minus A dagger, and that's anti-Hermitian. And so these generators naturally occur in both forms. If the group is compact, then if the generators are Hermitian, then this is a unitary matrix, and the group is compact, and so forth. Okay. Now, if the group is compact, so if G, well, the group is called G typically, if, not to be confused with Newton's constant. Anyway, if the group is compact, then the generators are Hermitian, and then FCAB is minus I over K trace of TATB TD dagger, this being the commutator, and that's the same as minus I over K trace of the commutator of TA with TB times just TD, because all the generators are Hermitian. And then what we have about a trace is that a trace is cyclic. And the basic rule is that the trace of AB is the same thing as trace of BA. And so when we say cyclic, what we mean is, for example, if there were a C here, then we move the B forward, and it looks cyclic like that. So, for the case of Hermitian, here we need to turn the thing. For the case of Hermitian generators, we have FB AC. So I'm starting out with FBAC. So this is minus I over K trace of TATC TB. Oh, let me just emphasize once again, this is the general case. Sorry. This is the general case. Notice it's got to be antisymmetric in the lower indices. So this is always minus FCBA, just because the commutator is intrinsically antisymmetric. Okay, so this is FBAC, and now if we use the cyclicity of the trace, this is minus I over K, trace of TATC TB minus TC TA TB. And now what we can do is we can move the B forward here, and we can move the C back, the TC back, and so we have minus I over K trace of TB, TA, TC minus TA, TB, TC. And now we see this is minus I over K trace of TB, TA, TC. But this for Hermitian generators or compact groups is by definition FCBA, and then since this is antisymmetric, this is minus FCAB. So we get this rule for the structure constants. Again, if they're Hermitian, if we have a compact group. So this is big G. If we interchange in this relation A with B, then what we get is F A. Let me get this straight. F A B C. So in other words, I'm having, F A B C, because I've interchanged A and B, and now we use those two, and we get F C A B equals minus FC BA. And now if we go back to this relation, namely this is equal to FBAC, we go back to this relation and we interchange B and C, then we get the rule FCAB is FBCA is minus FBAC. Well, if you put all those together, you see that the structure constants are totally antisymmetric when the group is compact. And so you have basically F, and in that case, since it's totally anti-symmetric, what I do, not everybody does this, but what I do, in fact, I think Weinberg stays with one upper index, but I like to just lower them all. Oh my goodness. Hold on. Yes,
Where is that house of bread?
I sent you a map. It's on Carlisle, just south of Indian School, and it's on the east side of the street.
Okay.
Bye. Sorry. My wife only calls me during class. She has just some sort of she's psychic. Okay, so in other words, this thing is totally anti-symmetric, so some people, me included, use this simpler notation. And then the thing is, then we say that F is totally anti-symmetric in the three indices A, B, C. Okay. Now, in fact, for compact Lie groups, the structure constants not only are totally anti-symmetric, they're also real. And to see that, we just take the complex conjugate of F, A, B, C, and that would then be I over K trace, and then we would have basically we're taking the complex conjugate of TA, TB, TC dagger, okay? But it's Hermitian, so we can forget the dagger, and we're taking the complex conjugate of that. And so this is I over K trace, and when you take the complex conjugate of a trace of something, you change the order, not that it matters, that becomes that, and this becomes TB, TA. I'm using the hermeticity and the way a commutator behaves when you take the complex conjugate. In other words, what I'm using here is the trace of A. Complex conjugate is the trace of A dagger. Okay. The dagger conjugates everything and interchanges. You know what I mean.
Yes.
Anyway, it doesn't matter with the trace. Okay. The transpose. Sorry. Okay. Now we get a minus sign out of here. The trace is cyclic, and so this is minus I over K trace of TATB, TC. And if we want, we can put a dagger there because it doesn't matter, the thing is Hermitian. And so this is also FABC, which is FABC. Okay, so the structure constants are real. I almost wonder whether maybe, as always, Weinberg's right to keep this C up there. But my notes aren't that way, so I'm going to stay this way. Okay, so basically, the bottom line here is if we have a Lie group, then the commutator of any two generators is I FCAB TC. It's a linear combination of generators with coefficients that are structure constants apart from an I. If the group is Hermitian, then the structure constants, if the group is compact, the structure constants are real and totally antisymmetric. All right. The next topic, let me get a drink of water. The next topic is gauge theory, and I like to do gauge theory very quickly in one simple example. And so let me just give you the essence of gauge theory. This, of course, is due to Yang and Mills. The basic idea was that you have a transformation where the fields psi prime of x is some unitary matrix that depends upon x is space-time. Okay, some four-vector saying where and when. And I write it this way because I don't want all these bloody indices confusing us. But what, if I put in the indices for the moment, this might be A, B, B. This is a unitary matrix. So, Yang and Mills developed gauge theory for compact groups. I actually wrote some papers about it before you people were born on gauge theory for non-compact groups. But I'm going to stick to the classic case of compact groups. They did this back in the 1950s. Okay, well, terms like psi dagger of x, psi of x, are automatically invariant because this prime is just psi dagger, u dagger, u psi. I'm using matrix notation and I'm dropping the x for the moment. U is unitary, so this is just psi dagger psi. So those terms are automatically invariant. The problem that Yang and Mills overcame was that you have in the kinetic part of the action looks like this. In other words, it's derivatives, it's the space derivatives dotted into the space derivatives minus the time derivative dotted in, times the time derivative and a Hermitian conjugation. And this isn't invariant under this kind of transformation because U depends upon space-time. So what Yang and Mills said, well, let's change this and call it dI of psi dagger, dI of psi, and require that under a gauge transformation, d of psi prime equal d prime psi prime, of course, but that this equal u d of psi, and I left out the space-time index of differentiation. In other words, the reason why this is invariant is that u goes into, is that u prime is just u psi. So they said, well, d psi prime is going to be d prime psi prime for sure, but it's going to be in fact u d psi. That was the key step. And then it's all downhill from there because you just unpack this, and what you get is di plus ai prime u. So that's, well, I maybe unpacked it a little bit too. Yes.
Tu sais combien coûte le pain? $8 pour un truc de pain.
Well, I don't remember the price, but what the hell, buy it. Mia will want some, so buy it anyway.
$8.
Jeanette,
Ok.
do whatever you want to do. As I said, only time should call this down. Otherwise, I'm completely ignored. Okay, so the essential idea here is that you want d prime, a d prime on u. You see, when this, what this actually is saying here, so I skipped a step I shouldn't have said. This is d prime u psi is equal to u d psi. Let's unpack this just a little bit. And now we have the same psi there, so really all we need is d prime u should be u d. So this is d prime u equals u, and it's just d. And we're writing di as ordinary derivative plus something else. And the prime hits to something else. This is in the book, of course. But maybe it's good to see it several ways. In fact, I did skip an equation in the book. So let's just unpack this a little bit. This is diu plus udi, because the derivative acts to the right and goes through the u as well. And then we have ai prime u equals udi plus uai. And so we cancel these two terms. And what's left is that ai prime u should equal uai minus diu. And now we multiply by u adjoint or u inverse, and we get the rule uai u inverse minus diu u inverse. And of course here, u inverse is the same thing as u adjoint, so you can do it either way. So this is the general rule, and psi prime is equal to u psi. So that's what Yang and Mills discovered, and I think their work was basically ignored for at least 5 years, and it wasn't. I don't think it was until the 60s that anybody took this seriously, and then they realized it was everything, almost everything. In fact, the standard model, all the interactions of the standard model, almost all of them, are due to an effort to keep the angulars, to have an invariance of this kind. And you see what you're saying here is that at every point in space you're changing what you call the components of your matter fields. The size of matter fields, typically fermions, but they can also be things like the Higgs boson. Now, in general relativity, what you're saying is that at any point in space, you could change what you mean by your coordinates. So you can have general coordinate transformations. And of course, general relativity actually was back in 1915, whereas this was 55, so that's 40 years later. People resisted the Yang-Mills transformation because it was very, very strange. It's one thing to change coordinates, but the Yang-Mills transformation, for example, maps a neutrino into an electron and an electron into a neutrino. And these things are very different. One is neutral, the other one is charged. One is almost massless, the other one weighs half an MeV, roughly. So that's why people didn't pay attention to Yang and Mills for a while. Okay, let's look at the rotation group a little bit, and the Lie algebra of the rotation group. Basically, the rotation group is some matrix R on, let us say, a 3-vector X, dotted into R on some other 3-vector Y. We can rewrite that as X transpose R transpose RY, and we can say that we want this to be the same as X dot Y, which is X transpose Y in another notation. And so what this means then is that R transpose R should be the identity. This is just a 3-by-3 relation. This means the determinant of R squared is 1, so the determinant of R is plus or minus 1. And now if we go to the Lie algebra, take the Lie algebra point of view, which is to look just near the identity where things are simple, we say R, we just said R equal to 1 plus omega, where this 1 is really the 3 by 3 identity. And so we have the rule 1 plus omega transpose 1 plus omega is equal to 1, or the identity, and now these omegas are infinitesimal, so we can ignore omega squared terms, and this just says omega transpose plus omega equals 0. In other words, omega is antisymmetric. So a 3 by 3 rotation matrix is just the identity plus any antisymmetric 3 by 3 matrix. And in fact, real 3 by 3 matrices, we're talking about ordinary rotations. Notice that we could be doing this in n-dimensional space. If we did this in n-dimensional space, then R would be n by n, this would be an n vector. Everything here would be the same, and we would just say that the omegas had to be n by n real antisymmetric matrices. And the group we would be talking about then would be ON. And so the particular group we're talking about here is O3. That's the ordinary rotation group. And now these omegas then are a linear combination of the 3 generators of or let us put it this way, there are 3 just linearly independent 3 by 3 matrices that are real and antisymmetric. And so there are 3 generators, and I wrote them down there in, I called them, I said omega B AC was epsilon ABC. And where epsilon is 1, if ABC is 1, 2, 3, otherwise it's 0. No. Epsilon is totally antisymmetric, and 1 if ABC is 1, 2, 3. But if ABC is 2, 1, 3, then it's minus 1. It's called the Levi-Civita symbol. Okay. Well, again, we have this absurd fetish in physics departments where we try to make generators Hermitian, so we write them this way. TB is I omega B. And then we can, let me go around to the front here. Let me say that we can now compute the commutation relations, or compute the structure constants, I should say. In other words, we've actually, well, we've sort of done things in sort of a kind of an arbitrary order almost. That is to say, we know the generators have to be these 3 by 3 antisymmetric matrices, and so we said, okay, these are they, what are the structure constants? And so the structure constants we got are the right structure constants. So in other words, what we'll be saying is, if I write on the dry part here, TA, TB is IF, ABC, TC. Well, now if we actually do the multiplication with let us say every T equal to I omega D, if you work out what that is, what you find out is that the structure constants FABC are just equal to epsilon ABC. In fact, they have to be proportional to that in the 3 by 3 case because there is only one totally antisymmetric 3-index tensor. Okay, so what we have then is that these things are I, epsilon, A, B, C, T, C. So that's how the rotation group goes. Now, in physics departments, of course, where not only do we have the I fetish, but we have an H-bar fetish. And so we say our angular momentum generator is H-bar TA, or I, H-bar, omega A. And those are the generators of angular momentum. These T's that I defined here as 3x3 matrices, and they're written there in equation 1088 explicitly. These generators are the generators in what we'll call the adjoint representation. And so maybe I should try, while we have 2 minutes left in this. So let me just skip ahead a little bit because we only want to spend three lectures on group theory is what we decided.
That's what I said, you can change that.
What?
If you want to go a fourth or a fifth, that's fine.
Yeah, well, it depends on what you guys want. Anyway, let me just mention something called the Jacobi identity. And it's A with BC. And if you, I won't go actually through the derivations, but you can check derivations in the book. You can check that it's this. And then what you get is the Jacobi identity, which is the double commutator, commutator of A with commutator of B with C is equal to the commutator of A with B, commutator of that with C, plus the commutator of B with the commutator of A with C. So that is the Jacobi identity. And there's another one involving the anti-commutator, but I think I'll skip that. And it turns out then that, of course, any three matrices, A, B, C, of any dimension satisfy this Jacobi identity. And consequently, the generators will satisfy it. TA, TB, TC will plus, I'm writing it slightly differently, TB, TC, TA, plus TC, TA, TB equals 0. So that's the general, that's the Jacobi identity for an arbitrary representation. If we now write this in terms of structure constants, in other words, this thing is I, F, let's see, what did I call it? FD sub BC TD. And you do that throughout. And then you do it for each term here. What you find eventually is that you find that F, D, BC, F, E, AD, plus F, D, CA, F, E, BD, plus F, D, AB, FE, CD equals 0. So if you redo this, you see what happens is you replace these two with structure constant times a t, but then you've got another commutator that gives you another structure constant, and then basically you get something that if you change indices, and it's something that's proportional to some to these the linear combination of the generators, they're linearly independent, and so you derive this relation. Now, it turns out that you can then do the following. You say TB AC, you just define this as IFCAB. And then you find that this relation here among the structure constants is the relation TA TB is IFCAB TC. And this, by the way, we're no longer in a compact group, this is a general group. So, because the Jacobi identity is perfectly general, and I use the general form of the structure constants. And with this identity, if you take, let F be that and substitute in here, you find that this is just the commutation equals that. So what that tells you then is that the matrices defined this way are generators of the same group. And this is called the adjoint representation. And in the case of the O3, we went directly to the adjoint representation because, well, the 3x3 representation is the adjoint representation. Next time, what I'm going to try to do is do the Lorentz group and say some things about the Lorentz group. And I may, if I remember, do a demonstration of the commutation relations of the rotation group. Have you all seen that? You probably haven't seen it. Did you see it? Something I do with a big sphere? Mm-hmm. All right.
I've seen the video of you doing it.
Okay. All right. Well, I'll do it anyway if I can. Okay, I think we can stop now because we're out of time.